Hi everyone! Today I'm going to be presenting for the University of Utah Virtual Symposium. My topic is something that I've been working on for my thesis, my honors thesis for the past couple of semesters, and it's about Noetherian property of invariant rings. So let's get started. First of all, I'm going to start off with talking about a bit about the background and introducing some key definitions. So the very first thing that we need to know is what is a Noetherian ring. And it's essentially a ring that has a specific property that can be described with three equivalent statements. One of the ways we can describe a Noetherian ring is a ring where all of the ideals of the ring are finitely generated. The other way we can say is that it satisfies the ascending chain condition, which means that all ascending chains of ideals must stabilize. And additionally, we can also use Zorn's lemma to make an equivalency to the statement, every non-empty subset of ideals has a maximal element. Let's introduce some examples of Noetherian rings. One of the simplest examples is a field. A field is essentially a ring where all of the non-zero elements have inverses, and so it's actually a fact that it has only two ideals, the zero ideal in itself. And so if we use the second definition second way of defining a Noetherian ring, which was satisfies the ascending chain condition, the only way we can make a chain of ideals here is for a field is by taking the zero ideal and then it's contained in the field itself, and that's definitely going to be going to terminate, and that means that it's going to be Noetherian. Additionally, a really nice example is a polynomial ring of finite variables over a field, and this is also Noetherian. We can also take power series rings over a field as well using finite amounts of variables. Power series rings are essentially we can also the elements look like infinite sums. Like the polynomials usually are up to a specific degree, like a finite degree, but here now we have like infinity. So what is a non-Noetherian ring? So a good example would be if we take a polynomial ring again, but this time we take infinite amounts of variables. And because of this, we can make a chain of ideals. So let's start with x1, the ideal generated by x1 is contained in the ideal generated by x1 and x2, and so on and so on. And this is going to continue infinitely because we have infinite amounts of variables. And so this chain is not going to stabilize, and so that means that this ring is not Noetherian by definition. Let's continue. We need to know what group fractions are. Let's say we have a set S and a group G. A left group action of G on S is a map that sends the pair G and S, like an element from G and an element from S, to an element of S. And what essentially is happening is we are sending elements of S to elements of S by treating the elements of G as functions. And so it needs to adhere to some specific properties as well, which means that the identity of the group has to be the identity map, which means that it will have to fix all of the elements of S, as you can see here. And additionally, it has to have the composition rule as well. So that's the case. Let's continue. If we have a group G acting on a ring by ring automorphisms, and we can do this, we just said, G is a group, S is a set, we can work on a ring, or G can act on a ring, R, by ring automorphisms, which means that there is a group homomorphism going from G to automorphisms of R. And automorphisms of R are essentially isomorphisms from R to R, and homomorphisms that are isomorphisms. Then the invariant ring is defined to be the set of all of the elements of R such that they are fixed under every element of G. And actually, this happens to be a subring of R, and this can be checked as well. And that's a really nice property. Let's continue. So initially, the idea that we're talking about, which is the question arose from Hilbert's 14th problem. The question can be simplified down to when can Noetherianity transfer to the invariant ring? So what types of Noetherian rings and what under which types of group actions can have a Noetherian invariant ring? And so there are a couple of limitations that we can put on a ring so that it does work. So as an example here, there's a theorem which states that if we have a finite group, G, and R to be a Noetherian ring which contains the rational numbers, then if G acts on R, the invariant ring RG is also Noetherian. And here it's actually using, in the proof of this, it's using Reynolds operator. As you can see here, it's a map from R to the invariant ring, and it uses a specific thing, which is the inverse of the order of the group. So the reason why our ring has to contain the rationals is because 1 over G, like 1 over the order of G, is not going to make sense as a number if R it does not contain the rationals. Like 1 over 2, for example, if let's say G is a finite group that only has 2 elements, 1 over 2 is not going to make sense because it might not live in the ring. And so this is essentially guarantees that we can use this map. However, this isn't always the case. Not every ring contains the rationals, and equivalently, you can also say when it contains the rationals, you can say that the ring is of characteristic 0. So characteristic is something that can be defined as how many times do you have to add up 1 to be able to get 0. And so as an example, in Zmod 7, for example, you need to take 1 plus 1 plus and so on 7 times to be able to get 0, because you get to 7, and 7 mod 7 is 0. And characteristic 0 essentially means that there is no number such that you can take 1 that many times and be able to get 0. So you can take 1 plus 1 plus 1 plus infinitely, and you will never be able to get 0. And so this is the type of ring that we're looking at here. Additionally, in another kind of related direction, Emmy Noether proved this theorem in 1926, which was if we take the ring to be a polynomial ring over a field, okay, and we use a finite subgroup of the general linear group, so GL and K, as you can see here, and act on R using G, this subgroup, then the invariant ring is also going to be Noetherian. And as a reminder, GL and K is essentially, it's a set with elements where the elements are n by n invertible matrices, and they act via matrix multiplication on elements of R. And so where do we send x1, x2, and so on at xn? You can figure that out by doing this multiplication. So let's continue. The most important thing here to understand the goal of my research was to not talk about subclasses of rings where it does actually work, because that has been studied quite extensively, but to figure out a much larger subclass or class of rings such that it's going to be counterexamples. So we were trying to find a class of counterexamples. What this means is I'm trying to find rings so that they are Noetherian, and we're trying to find specific finite groups that act on them, such that they're going to be the invariant rings that we get is going to be non-Noetherian. And so Nagarajan was a mathematician who first came up with a characteristic 2 counterexample. It was a very very nice kind of simple way, not necessarily simple, but this is a very good way of going about it. So we start off with a p prime integer, and this is a generalization of Nagarajan's characteristic 2. So here we are working with characteristic p, and this was the goal of my research, which was to take the characteristic 2 counterexample and expand it and generalize it to characteristic p, where p is a prime integer. So to present the general version, we are going to take the field to be the field of fractions of these infinite amounts of variables. So you see we labeled these variables to be a1, b1, a2, b2, and so on. And we are taking it over z mod p, so integers mod p. And this is going to be a field, so field of fractions is always going to be a field. And we are taking the ring to be a power series ring of two variables over this field. And as you might have noticed, the reason why we are counting these variables like this, the reason why we labeled them like this, is because this is a simpler version using only dimension 2, so only using two variables, but this can very easily be generalized to x1, x2, and so on. However, the generalization here, the importance is here is on the characteristic. So what we can do here is we define an automorphism, sigma, going from R to R, where first of all, it fixes X, it fixes Y, and we have a special type of kind of polynomial, Pn, where it can be described as an x minus Pn y. And we are defining sigma to send an to an plus y Pn plus 1, Bn to be sent to Bn minus x Pn plus 1. And then I claim that the invariant ring under this group action, where the group is going to be the group generated by sigma, so it's going to be just a bunch of, sigma, sigma squared, sigma cubed, and so on. This is going to make up a group, and if we use this group to act on R that we have given here, then the invariant ring is not going to be Noetherian. And some of the things that are going to be useful to see that, well, first of all, we can show that the group that sigma generates is going to be a finite group from these properties. Well, first of all, it can be shown that it fixes the polynomial that we showed. It fixes Pn. It also fixes an if we take it to the power of p, and same thing for Bn. And as you can see here, it is going to be essentially a cyclic group where we get an isomorphism to z mod p, so integers mod p. And as you can guess here, the number of elements it's going to have is just p. So this is essentially the conclusion of my talk. These are some of the references, and I wanted to say thank you for listening up to this point. Hopefully there were not too many confusing parts. If you want to check out my research, I will probably be finishing typing up my thesis very soon. Thank you to University of Utah, and thank you for UROP for sponsoring me last semester to be able to do this project, and being part of the undergraduate research community at University of Utah has been a very nice experience. And yeah, hopefully everyone has a good day, and thanks so much. Again, bye.